Okay, welcome back. Drum roll, please. Thank you. All right. Here is a function. It's a cubic function. Hopefully you recognize that. Starting low, ending up high. Two turning points, degrees 3, turning points 2, point of inflection, there's one of them. Right? Remember that year 11 assignment, which everyone does, I assume Unley does. Anywho, what we have in this cubic function is a combination of two shapes, right? Because we've got concave down here. And then there comes a point, I've marked the point in blue, a point of inflection, where that concave down shape changes and becomes concave up. Excuse me. Right, so concave down, concave up. Now, what I've done is introduce a tangent equation, just using the formula from your book, right? So the derivative of our function times by the change in x plus the function value, right? F of x at point A, and I've set A to range between 0 and 4. So we're starting over here, and we're pretty uphill, right? And I just want to look at this concave down bit. So I might set the range to only go across to 2, and let's see what happens. Right? So we start very uphill, and oh. We're still uphill, but where our gradient itself is decreasing. And you should be able to see it. It's quite clear when you've got the tangent. When we get up to the maximum, the local max, the gradient has gone from being very positive to 0, and that happens exactly on 1. Right? And that's something you already know when you have the first derivative and you make it equal to 0, you're finding maxes or mins, or possibly points of inflection as well, but only if they're stationary points of inflection. And as this continues, let's just go back to the start again. So here, gradient itself is decreasing, gets to 0, and then it keeps decreasing until it gets to that point of inflection. All right. Now if I play all the way across to A equals 4, right, let's try that. So we've got decreasing gradient, gets to this point of inflection. Now the gradient starts to increase. Okay, can you see that? Let's do that again. Right. So we've got a decreasing gradient when we have concave down, but there comes a point at A equals 2, in this case, where our gradient stops decreasing, the gradient itself stops decreasing, and then the gradient starts increasing, and that corresponds to this change in shape, concave up. From this point, let's go. So now gradients start increasing, right? Now down here, the gradient, it's still negative, but as we work from left to right, the function's downhill, the gradient is negative, but as we're going from left to right, the gradient itself is increasing in its value. Right? It's going the wrong way. Now get it back to start. Right. So where was I? I was about here. The gradient starts increasing. Right? Now, maybe we could look here, I've made our x value or our a value equal a half. And I did that because at this point right here, x equals a half, I reckon I've got a gradient of exactly 4. Across 1, up 4 squares. So the gradient value there is 4. But what I'm saying is that the gradient is decreasing. Right? So if I move a little bit further, maybe to there, now the gradient looks like it's about a half. It's gone from 4 down to a half. That's a decrease. Okay. All right, let's get rid of that. I want us to now think about what would the first derivative look like. Okay, maybe we can start with our stationary points. There's one there, there's one there. Right, our derivative has to be 0 at those points. So if I was graphing the derivative, it's going to be 0 there and there, right? Because the derivative is the gradient function. Here, the function itself is uphill. I'll have positive values for the gradient. So maybe the gradient function is coming down there somewhere until it gets to the stationary point, the max, and hits 0. Now the function goes downhill, all right? So the gradient here is negative, and it's going to be in this region until it gets back to 0 at this minimum. Then the function increases. We've got an uphill function in this part, and we'll get positive gradients up there. Right? Here is a picture of the gradient function. One thing to notice is that we've gone from cubic, right? In the function, the red, we had degree 3, we had a cubic. In the gradient, we've got a parabola. We've gone to x squared, as you would expect when you differentiate. And notice that the point of inflection, where it changed from concave down to concave up, that point of inflection is actually a minimum in the gradient. Okay. Now that point of inflection, if we think about this, the gradient here is decreasing, but gets to a point where it turns the corner and it starts to increase. Just at this instant, the change in the gradient there is 0, right? And we can see this in the second derivative. So the point of inflection, this is really key, right? The point of inflection can be identified when the second derivative equals 0. How do I find the point of inflection? I make the second derivative equal to 0. How do I find stationary points on a function? I make the first derivative equal to 0. How do I find points of inflection? You make the second derivative equal to 0. Right. Okay, I just stopped there for a little drink of water. Now, one more thing about this. Hopefully we've made it really clear that the point of inflection is where the second derivative equals 0. Okay. But I want you to now think, well, why is the second derivative negative when we have concave down? First, you've just got to learn that. The concave down shape indicates to us, or can be indicated by a negative second derivative, right? And this can actually be used in optimization questions. You could say, this point here, if I was to plug in x equals 1 into the second derivative function, I would get a negative answer. That would indicate, therefore, that I have concave down shape, which then, therefore, indicates that that must be a maximum value, right? So across this region, where we have negative second derivatives, we have a gradient that is becoming more and more negative. So the second derivative is indicating to us the rate of change of the gradient. All right? The second derivative is telling us that as we move across with our x values from left to right, that our gradient itself will become smaller and smaller, or negative, right? Hence the negative values, until we reach the point of inflection, right, where the second derivative is 0, and then we have our concave up shape. Concave up means that our gradient is starting to become more and more and more positive. So the rate of change of this gradient is positive from left to right, and that's reflected by positive values for the second derivative. Once again, if you're doing optimization, right, you could show that that's a local minimum there where x is 3. You could show it with a sign diagram of the first derivative. Here's the first derivative. And at that point there, the first derivative goes from negative to positive on the sign diagram, downhill to uphill, right? We've got a local minimum. But you could also look at the second derivative at x equals 3 and say it's a positive value. And what you want to, I guess, memorize or be able to think through is that concave up shape has positive second derivative because the gradient is becoming more positive. The rate of change of that gradient is increasing.